Okay, so we are recording. We are now looking at another example in section 6.6. 6.6 is applications to physics and engineering. And in this example, we have a tank that has a shape of, it's another tank problem. We have a tank that has the shape of an inverted circular cone with height 10 meters and base radius 4 meters. It's filled with water to the height of 8 meters. Find the work required to empty the tank by pumping all the water to the top of the tank. And now they're telling us, so now we're dealing with metric units. Metric units, okay? Not English units, but metric, not American units, but metric units. So the density of water is 1,000 kilograms per cubic meter. So let's see here now. First, as always, let's get a picture of the situation we're dealing with. So if I go down here to figure 3, there's a picture of this inverted conical tank. The tank's 10 meters high. It has a radius of 4 meters. And what they're showing there is water filled into the tank. And the water is filled up to a height of 8 meters. So the top 2 meters, there's no water there. And what they do is, just like with the previous problem we looked at, tank problem we looked at, they're going to take a layer of water. That purple layer of water there is with a height of delta x, and that purple layer of water is xi meters below the top of the tank. Okay, so you know, the diagram is very good, and you'll notice that the ith layer of water is in the shape of what? What is that ith layer of water in the shape of? It's not a box, the ith layer of water for this problem. It's not in the shape of a box, and it's the shape of a disc. That's right, or a cylinder. Good, 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 Susanna, good, Victoria. So, of course, we know we need to find the volume for the ith layer of water. And the volume of a cylinder is pi times r squared times height. So what do we need to find? Well, we have the height as delta x, but we need to know the radius. And the radius is dependent the radius of the ith layer of water, for that cylindrical ith layer of water, that radius is going to be dependent on how far down you are from the top of the tank, the distance x sub I. So just like the last problem, we can make two similar right triangles to help us. And so they do that here in figure 4. There are two similar right triangles. The big right triangle has the height of 10 meters and radius of 4 meters. And then the little right triangle has a height of 10 minus xi meters, and then a radius r sub I. So you see, we can set up based on similar right triangles, we can set up a proportion and solve for that radius. Are there any questions so far? Okay, well then let us proceed on. So if we take in figure 4, if we take the radius and divide it by 10 minus xi, that would be equivalent to taking, that would be equal to 4 divided by 10. Okay, so little radius over little height is equal to big radius over big height. And here then is that proportion. And we can solve for the radius in terms of the variable x sub I. X sub I, remember, is the distance that the cylindrical ith layer of water is from the top of the tank. So the radius is equal then to 2/5 times 10 minus xi. Okay, You solve that proportion for R, you'll get 2/5 times 10 minus xi. And so now we can find an expression for the volume of the ith layer of water. And there it is. So the volume of the ith layer of water is pi r squared times delta x. Well, r was 2/5 times the quantity 10 minus xi. If we square that, we're going to get, I mean, maybe I can show that real quick. Hold on. Let me just show that in the whiteboard real quick. So, you know, if the radius is 2/5 times 10 minus xi, then radius squared would just be 2/5 times 10 minus xi, the whole thing squared. And that's just 2/5 squared times 10 minus xi squared. And that equals 4/25 times 10 minus xi squared. Okay, and so right, this is r sub I. So now if we go back to the book, here. Hopefully now that volume expression they have, 4/25, well, yeah, 4 pi times 4/25 times the quantity 10 minus xi squared times delta x, that hopefully makes sense. Now, what are we going to do with that? Well, after we find the volume of the ith layer of water, we're next interested in finding the force on the ith layer of water. What is the force of the ith layer of water? And since we don't have pounds in this problem, we have to work with the gravity. So how many remember that density is equal to mass divided by volume? How many remember density equals mass divided by volume? Maybe from high school, that formula. Sure, Mark remembers that. Clea remembers that. Well, if density is mass divided by volume, okay, then if density is mass divided by volume, then mass is density times volume. Well, the volume we know, and the density in this problem, they said density of water is 1,000 kilograms per cubic meter. So to get the mass of the ith layer of water, we will take density times volume and get 160 pi times the quantity 10 minus xi squared times delta x. Now, why do we need to find the mass? Well, because of Newton's second law, force equals mass times acceleration. Only this time we're using the acceleration due to gravity to overcome the force of gravity. So in that case, let me just maybe highlight this. I can hide and put that there. So now force is mass times gravity. Well, gravity is 9.8 meters per second squared. That's where the 9.8 comes from. How many recall has anybody heard of 9.8 meters per second squared for acceleration due to gravity? Okay, Susanna recalls that, and Clea recalls that. Okay, well, great. Well, okay, so now I'm going to find the force for the ith layer of water. And when I work that all out, I'm going to get 1,568 pi times the quantity 10 minus xi squared times delta x. That's the force for the ith layer of water. So now we have the force for the ith layer of water. What do we need to know next about the ith layer of water if we're going to find the work to raise the ith layer of water to the top of the tank? We know the force. That's right. Good, Mark. Good, Jonathan. Distance. We need to know the distance. Well, in the picture here, the ith layer of water. Okay, the ith layer of water, and this is what we're using. We gotta stick to the picture we used. The ith layer of water is that purple ith layer of water in Figure 3 is xi meters from the top of the tank. So therefore, in finding the work, okay, finding the work. So we know this, but now the work, okay, to raise the ith layer of water to the top of the tank is equal to then force times xi. Force of the ith layer times the distance the ith layer is from the top of the tank. And that's going to get us 1568 times pi times xi times the quantity 10 minus xi squared times delta x. Are there any questions so far? Some of your homework problems will deal with, you're going to have different units, and you have to be comfortable with both. Foot pounds and joules, and anything else that goes with those. Okay, well now that we know the work needed to bring the ith layer of water to the top of the tank, we're gonna add up all the work values to bring up the ith layer of water to the top of the tank. Okay, so we're gonna take the Riemann sum as I equals 1 to n. Now again, that's taking the water and breaking it up into n layers, and every layer, the work needed to bring that layer to the top of the tank is 1,568 times pi times xi times the quantity 10 minus xi squared delta x. Okay, we're going to let n go to infinity. The Riemann sum becomes the integral. Okay, so now you'll notice the limits go from 2 to 10. The limits go from 2 to 10. So let's just go back to the picture here and look at that real quick. So why do the limits go from 2 to 10? Well, the top layer of water is how far from the topmost layer of water is how far from the top of the tank. How far does that? I'm sorry? Say again? 2 meters. That's right. Good, Clay. And the bottom layer of water, at the very bottom, how far is that layer of water to the top of the tank? How far do we got to move that layer of water to pump it out of the tank? That's right. Good. 10 meters. And all the other layers are somewhere in between 2 and 10 meters. So that means then that your hold on here, one moment. Let me highlight. There we go again. There's then the limits go from 2 to 10. No, Susanna, you couldn't say from 0 to 8 because of the way that we defined x. Good question. If you go back to the picture there, the way they defined x in this problem is x is see on the left in Figure 3, that x sub I star there on the left. X sub I is the distance the water level is from the top of the tank. So given that, then the limits have to go from 2 meters to 10 meters. Do you see that? In Figure 3? Yeah, well, the water has to be moved, the top layer of water, right, not the space, the top layer of water there, that blue water, that top layer of water is 2 meters from the top of the tank. And at the bottom there, the bottom of the tank where the water is, that water's 10 meters from the top of the tank. Yeah, it's the water. I got to be careful. It's how far you move the water. That's what it is. The distance you move the water. That's right. So that being said, then, here's how you will get the work. So it's an integration problem. And you see, without calculus, you can't do these kind of problems, right? You can't do these kind of problems. I mean, calculus really helps us do a lot of cool problems. How many think this is pretty cool? What you learned today? These work problems. Okay, John's liking them, and somebody else said too that John's liking them. Man, just one person? Do we have a couple other? All right, thank you, Gabriel. Thank you, Mark. All right. I'll have to give out some virtual cupcakes or something if for people that say yes. Okay, on that note, are there any questions before I stop the recording? Okay, I'm going to stop the recording then. Very good.